Okay, let me start. In this lecture, I would like to talk about some important attributes for a digital modulation scheme. So these attributes are very important to decide how good your digital modulation system is. Okay, how good or how bad it is. So in the previous lecture, if you recall, I have discussed different modulation schemes and different constellation diagrams. Say this is 8 array quam and this is 32 array quam and 8 cross quam, 32 cross quam. There are many patterns, and here look at, there are some patterns here in the upper quadrant here, very less no the signals are like this, and here also signals are like this, and here it is something different, and this is 16 array quam, 64 array quam, then this is 4 array psk, and if you come back here something different, and here something different. So there are many possible methods where you can design your constellation signal constellation diagram. So when I have this choice of modulations available or choice of signal constellation, I should know how I can design the constellation in any particular manner, or some constellation looks like very interesting to me, or that might fascinating me. So one should naturally ask, is there some pattern behind this? On what basis should I design this constellation diagram? And what way I could put the points? Suppose one person can say, no, I may put the points like this, and some other person will come and say, no, you put the points far away from here. And what is the difference between these two? So that we should find out on what basis you are going to put the points in the constellation diagram. Essentially, this point is nothing but this is the signal. Let's say this is S1 of t and S2 of t, and this is S3. I'm writing randomly S4 of t. There are four signals. So how do you design these four signals? On what basis you are going to do that? So should we consider some parameters when you are designing this constellation? So what are the parameters should I consider? So that is an important thing that we need to address. So what are the parameters that we are going to look at? So therefore, what I'm planning is, let me first list out these parameters, okay, one by one, and what the parameters about, and later on how this parameter will help us to judge our system is good or bad. Okay, so the very first parameter is average energy per symbol of a signal constellation. Average energy per symbol of a signal constellation, of a given signal constellation. Before that, let me 1 minute, just to hold on. There is a grid actually, I need to activate that. I don't know where it is. Let me check. It is not there. View. Yes, grid. So this would be much better to write. That's it. So that I can write in a straight line. Fine. So average energy. So average energy per symbol of a signal constellation, because I couldn't write properly in a straight line, so it's better to have a grid. Fine. So let me first define average energy per symbol of the constellation. So given constellation, how much energy on an average that I'm using. So we have given a signal constellation. So let me take like this simple constellation. Let me take it. So there are 4 points here. So how much energy on an average I'm going to transmit. So let us consider this constellation. Okay, I have 4 points in this, 4 symbols. So essentially it has 4 symbols here, and corresponding to possibly 2-bit sequence, because this I can say, as I said, this is let's say 1 1, this is 0 1 0 0, and 1 1. You can take like this also. Let's say 1 point is you put here, 1 point here, 1 point here, 1 point here, put 1 point here, 1 point here, 1 point here, and 1 point here. So there are 8 points, 8 symbols here, 8 symbols, and each symbol you can map a 3-bit sequence here. Okay, you can take any one. Now what is average energy per symbol associating with this constellation? because different symbols have different energies. So let me take this one. This is best to example, best to explain. So this symbol will take some amount of energy and this symbol will take some other amount of energy, that I don't know. Maybe let me redraw this for one second, because it is something. I'll draw it properly. So I'll put 1 point here and 1 point there. Let me put 1 point here, 1 point here, and this I will delete it. Okay, now look at here. Now if you find the energy of this is different from energy of this guy or energy of this guy, therefore different symbols have different energies. So first thing we wanted to define the concept of average energy. So first of all, how do you find the energy? We know how the energy formula, what is the energy, right? So energy, we know in the case of discrete, in the case of DC we can say voltage times current times time. So if you take let us take this, all are voltage waveforms. This symbol, the point indicates voltage waveform. So therefore this is voltage times current equal to again voltage by R times T, and let us assume the resistance R equal to 1 ohm here. So it is V square times T, and this is the formula for DC case. Suppose if you have AC, then what you do is you take, instead of V, I have the voltage waveform V of T, and square it and integrate from 0 to the symbol interval and dt. This is your energy. Now what you do, you take this T equal to 1 second, and let us assume this is constant in that duration. So therefore this I can say V square. I am assuming this is constant just for to make it simple, that's why constant. Okay, constant, because we are assuming the constant amplitude, therefore in that particular duration, especially in quadrature amplitude modulation or QPSK, we assume that the amplitude is constant. Therefore this is V square, and integrate from 0 to T with respect to dt, then you'll get a T, and this T is assumed as V square times this T equal to 1. Therefore this is your V square. Therefore energy I can say V square. So what is this V square? This V square is the point how far away from the origin. Therefore if you have the points like this point is how far away from the origin. This is your V square. This is your V voltage, actual voltage, resultant actually. So this is x axis and this is y axis, and take the resultant. That is your resultant. Therefore the energy is equal to resultant square. Resultant square. You just take the resultant square. So therefore energy equal to resultant square. Energy equal to resultant vector square, or magnitude of the resultant, and take square. Let me write down here. Energy is equal to magnitude of the resultant vector and take magnitude and square it up. Okay, and square it. This is my energy. Okay, therefore if you take this constellation, I already drawn this one. I have 2 points here and 2 points here. It's a symmetrical actually. I take 1 point, and then 1 point. This is your real axis, and this is your imaginary axis, right? So imaginary axis. Now how do you find the resultant? This is my resultant vector. Let me write down the resultant vector. This is x axis, and in terms of y axis. So the x axis I will represent like this is let's say constellation point C1, this is C2, C3, C4, C5, C6, C7 and C8, like constellation 1, constellation 2, constellation 3, constellation 4, constellation 5, constellation 6, constellation point 7 and constellation point 8. Therefore the C1 has a real part, C1 vector has the real part plus j times imaginary part. So let me call the real part as C1R and the imaginary part as C1I, like this. Okay, so therefore what is the magnitude of this one? The magnitude is going to be square root of C1 r square plus C1 I square, and take the square of this magnitude. C1 square equal to C1 r square plus C1 I square. C1 I square. So this is the, and this one essentially indicate energy of the constellation point C1. Energy of the constellation point C1, right? Therefore, in general for M, I can write energy of the pulse. So this I can say Cm r square real part of that plus Cm I square part of that. So this is the energy of mth constellation. Energy of mth constellation. Okay, so what is the total energy? Total energy equal to C1 square, energy of the first constellation, energy of the second constellation, energy of the third constellation, and up to Cm square. This is my total energy, right? Now what is the average total energy? Average energy per symbol. So totally how many symbols do I have? Capital M number of symbols. Therefore this divided by C1 square plus C2 square plus up to Cm square whole divided by total number of symbols. Okay, now if you want to write in the compact form, let me write 1 over m summation over I equal to 1 to capital M. Okay, I'm sorry, small m, because the index is different. M equal to 1 to capital M, C1 square plus C2 square plus and so on. I'm sorry, again I'm doing mistake. It's not Cm square. So it is Cm square, right? Or you can say 1 over capital M times summation M is equal to 1 to capital M. The real part, you can replace this guy by Cm r square plus Cm I square. Okay, and take whole thing. And let me denote this average symbol energy as EC. Okay, this is average symbol energy per for a given constellation. Average symbol energy, average energy per symbol. I'm sorry. Average energy per symbol. Okay, and in that way we are defining this. So you can appreciate this energy for individual symbols will essentially on the amplitude of the individual symbols. Okay, and then this energy depends on the distance of the symbol from the origin. How far you are away from the origin, that will indicate, that will denotes the, or that will decides the energy of the symbol. If you are far away from the origin, then that means you are pumping more amount of power. So the distance you can think of is the sum of the square of real component plus square of the imaginary component. So the real component will be represented by CMR and imaginary component is denoted by CMI, C sub Mi. So this is the average energy per symbol for a given constellation. And the important point to note down here is, we assumed that all symbols are occurring equally likely. Okay, all symbols, otherwise this formula will not be valid. Okay, all symbols are equally likely. What is the meaning of this? The probability of C1 is equal to probability of C2 is equal to and so on, probability of C sub M, which is equal to 1 over capital M. Each symbol occurs with the same probability. And again, this statement would be true provided that only if every bit occurs with the same probability independently of every other bit. That means what? P of 0 occurs independently with p of 1, and this p of probability of 0 is equal to probability of 1 equal to 1 half. So if these two conditions are satisfied, then this is okay. Okay, so this is the first attribute of a given signal constellation diagram in the complex plane. And the second one is, this alone will not suffice, because at the end I should know how much amount of energy I am going to transmit for a given bit. So instead of saying no per symbol, because in one modulation scheme I may transmit 3 bits for a given symbol, and another modulation scheme I may transmit 2 bits for a given symbol, and another modulation scheme I may transmit 4 bits for a given symbol. So I cannot say energy per symbol, it will not make much sense. So to make more sense, what we can say is how much energy I am going to transmit for a given bit, for a bit, for one bit, how much energy that you are going to transmit. Therefore the next parameter is average energy per bit. This is very easy attribute to calculate, average energy per bit. So how much energy I am going to spend. So this is very important parameter, okay, and most important parameter, so is the average energy per bit. Now we will denote this average energy per bit by E, capital E sub B, okay, and it is a fairly standard notation, EB, energy per bit. Now this energy per bit equal to, so you know how much amount of energy you are spending per symbol, so that is EC. And how many bits do we have per symbol? Log m to the base 2, okay, log m to the base 2. So this many number of bits I am using in every symbol. Like suppose if you say QPSK, so how many bits we are using? 2 bits, that is 2 power k is equal to 4, where k equal to 2, k equal to 2, that means 2 power 2 is equal to 4. This is my m. So you take log base m, that is log base 2, log 4 to the base 2, so which is nothing but 2 bits. Therefore in each symbol I am using 2 bits. So this is a formula to calculate energy per bit. So average energy per bit is given by E sub c over log m base to the 2, or in fact simply you can say EC over k number of bits, where k is the number of bits which you are using in the in each symbol. So this is as far as the energy definition is concerned. So next parameter which is of interest is minimum distance, and this is a very important parameter of a given constellation, okay. So minimum distance, and the very name itself will tell you what it means, okay. So it denotes the smallest distance between any 2 points on the constellation. Let me take points like this. Maybe I will, if possible, I will insert the diagram. No, it is not activating. Okay, I'll draw the figure. Yeah, it has come. Pictures. Let me introduce some complex constellation so that it's easy to. Maybe let me try this one. Yeah. Now look at this figure. Now in this, Now this is the distance. You can take 1 minute. I will go to draw. Fine. Now this is a distance. Let me take d1, and you take this one. This is some d2. Maybe this is equal. Okay, d3, and you take this distance d4, and you take this distance d5. You find the minimum distance among all possible pairs. Okay, that is called a minimum distance. So this is a given constellation. In this constellation, you take all possible pairs, or you can take this point and this point, find the minimum distance, or you can take this point and this point, find the distance. So which distance is minimum, that is called a minimum distance. Okay, so it denotes the smallest distance between any 2 points on the constellation. You take any 2 points, the choice is yours, but the distance should be small. It should be the smallest. That is called the smallest distance. So the definition is given by minimum distance equal to minimum distance is given by smallest Euclidean distance Euclidean distance between any pair of distinct points. Any pair of distinct points on the constellation. On the signal constellation. Okay. So you can write a mathematical expression for it. It's very simple. So let me denote this minimum distance by d min. Where is it? Yeah. So let me denote this minimum distance by d min. So your d min is equal to the minimum distance. You take the minimum distance. Like now, how do you find the minimum distance? You find, let's say this is one point and this is one point. You find the difference of these 2 points. How do you find the difference? You take this part and this point, and maybe let me take another figure. Let's say one point is here and another point is somewhere here. Okay. So how do you take the distance? You find this point, like let's say this is x1 y1 and this is x2 y2. So distance is x2 minus x1, right, the whole square, plus y2 minus y1 the whole square, which is equal to distance. This we know, simple formula. So similarly, so x is a real part and y is a imaginary part. Therefore Cm real part, mth is our constellation Cm r minus Cm prime r. Let's say this point is Cm and this point is Cm prime whole square plus C sub m I imaginary part whole square minus C m prime I whole square, and this is d min square. Okay, so maybe I'll write down one more very clearly here. So d min square equal to the real part x2 minus x1, that is Cm r minus Cm prime r whole square plus C m I minus Cm prime I whole square. So, and take minimum of this all. You take minimize over all. This is the distance. You take minimum of this, where m is not equal to m prime. So this is your d min. So minimum of this value for all possible combination of the indices m and m prime, and m prime are not the same. They are different, distinct points. So you should consider distinct point, all possible combinations. So that's the formal definition of the minimum distance on the constellation. Now, now one can ask, is it sufficient, this d min? Okay, if you ask this question, the answer is no. Okay, so this is a very important parameter of a signal constellation, but unfortunately this minimum distance parameter alone will not suffice, because I can have 2 signal constellations. Maybe I'll draw the constellation. See, I have the constellation like this. I'll put the points like this. Okay, and put one point here, put one point here, then let me draw like this. Now what I do is the same thing, I let me draw like this. So I put 2 points here and 1 point here, 1 point here, and here also 1 point here and 1 point here, and 1 point here and 1 point there. Now see, this is a smallest one and this is the biggest one. The shape is same in the both the figure. Shape is same, but the d min is different, right? I can have 2 signal constellations. See, this is a constellation 1 and this is a signal second constellation. This is the first constellation. The shape is same. The shape is same. Okay, identical in shape, but how different d min. Here d min is something, let's say some value, let me call x1, and here the d min is some value, let's say x2, and x1 is not equal to x2, and perhaps x2 is greater than x1, some values. Okay, So that means what? I am simply spacing out one constellation more than the other. See, I am just simply increasing this distance, increasing the distance, increasing, and this distance also increased up, and this distance also I am increasing, simply increasing the distance, but that will not help me in any way. So one constellation, that means what? If I increase the distance, essentially you are increasing the resultant vector magnitude, right? If you increase the distance, see, this is the distance from the origin and this is the distance from the origin, but here the distance is very long, distance is more. If distance is more, means more voltage. The voltage is resultant vector, because this, after all, this point is a voltage waveform, right? Voltage waveform, it indicates amplitude of the waveform. So if you increase the distance from the origin, that means you are pumping more amount of power. So if you increase the space out the points in the constellation, that indicates that you are increasing the more you are pumping the more amount of power than the other. So that is a power advantage. Okay, so that's not a constellation advantage. In constellation wise, I cannot say this is better than that. I can increase the d min of two constellations which are in identical shape but are different from each other, in the sense that one has points which are spaced out more than the other. They are identical in shape. That will not help me. That will not help us. So I can increase the minimum distance by simply pumping more power in the system. Okay, so but putting more power in the system is alone not good. Okay, so therefore we need another parameter or another good measure. Okay, so with that you can say the system is how good the system is. Therefore, because you must normalize it with respect to, and therefore you have to normalize it with respect to something which will otherwise make them similar. So see, this is also similar to this one. So the first constellation is similar to the second constellation. Therefore, to obtain a proper figure of merit, the people generally call figure of merit for a constellation, we define something what is called a rho mean, normalized minimum distance. Okay, this is normalized minimum distance. Normalized minimum distance. Minimum distance. Okay, therefore this rho min is called figure of merit. It is denoted by rho min, and this is defined by rho min is equal to your d min over E sub b. Okay, we call this normalized minimum distance. So basically what we are doing is we are finding the minimum distance which has been normalized by the average bit energy. So we call it normalized minimum distance. Just to give you a feel for what kind of values we'll have for a figure of merit. For example, if you take dpsk, this is 0, and let's say this point is a and this point is minus a. What is the d min here? D min is equal to 2a, difference between these 2 points. What is the energy? Energy per bit you can calculate. Okay, and now I am rushing through, so you can do this. Okay, energy per bit, energy per symbol by number of bits. You are after all using your single bit, and you can find out the energy is a square. In fact, I can say a square, and per bit is the number of bit is 1, and you can substitute that and d min, and then you find that this is actually d min and energy per bit. Then finally you will end up with, let me say, I think there is some slight mistake. I think rho min square something, so let me check it out. Okay, so this go through this rho min minimum distance. So this rho min square equal to, let's say this normalized distance is like a rho min square. Okay, rho min square equal to hold on 1 minute, is it d min or d min square? Okay, so rho min square equal to 2 for psk and qpsk. That this you can check it out. Okay, you can work on it, and you will come to know. And it is always less than or equal to for other signal constellation, signal constellation. other signal constellation. So and you can convince yourself that this rho min square equal to 2, um, it's 2, and it is going to be less than or equal to for all other constellations, and you can work on it. You take any QPSK or some other constellations, let's say 8 PSK, 8 array PSK, and you can find out this rho mean square. This is always less than or equal to 2. I'm sorry, not 1, it is less than 2. Now you can ask, why is this rho min square is so important? Because at the end of this lecture series, like we will compare different modulation digital modulation schemes, and we will we'll do the comparison based on a parameter called probability of error, which digital modulation scheme gives very low probability of error than the others, than that of other digital modulation schemes. So therefore, ultimately in a digital communication system, the final performance measure is the probability of error for a given system or given modulation scheme. Therefore, here we are talking about the contribution of the constellation design in determining the probability of error. That means which constellation will give you the minimum probability of error. So I cannot go and keep on look at this constellation diagram, that constellation diagram. It's very tedious. So what do? Is I will evaluate the probability of error in terms of a parameter called rho min square and energy per bit EB. So these two parameters I will use to find the probability of error. So therefore the probability of error is a function of two parameters. One is rho min and another one is EB, how much energy I am going to use it. And this calculation is based on the under the condition something called a Gaussian noise situation. So when the noise is Gaussian, how much error I am going to get for a given constellation or for a given digital modulation scheme. And for a typical value like if rho min square is large, then you will have a smaller error probability. So generally, if you make it rho min square is large, then this implies low probability of error, low P probability of error. Okay, and if rho min square is small, then we will see why this is this kind of things happens. When rho min is large, then low probability of error, and low min is small, then large probability of error when we discuss digital demodulation. When I say rho min is large, that means one point is far away from another point. So it's very less likely that this point becomes this point. Therefore, the probability of error is low in this case. P is low. Now, if I have these 2 points very close by, now here this rho min square is less. Therefore, here the probability of error is more. That's a intuition point behind this. So here we are talking about the contribution of the constellation design in determining the probability of error. So that turns out that if you look at the error probability PE in a Gaussian noise situation, the error probability depends on the signal constellation design, how you effectively or efficiently or cleverly you are designing the points on the complex plane. Okay, so essentially evaluation of that constellation is essentially depends through this parameter rho min square. Therefore, the error probability P depends essentially through this rho min square. So the final point which I want to write down here is probability of error in Gaussian noise depends on the constellation structure. Essentially through the parameter rho min or rho min square, whichever you like, you can take it. So this is a useful measure by which you can compare, as I said, different signal constellations. Okay, you may like to look at different constellations and you can compare it. Okay, if the constellations are well designed, then they will be such that any 2 points are placed together will have a large minimum distance. So you design constellation points such that make sure that it has very large minimum distance. And again, if you make it very large minimum distance, that means you are pumping more amount of power. So one has to trade off between this the amount of power which you are spending to transmit the data, as well as the probability of error. Okay, so we look at this error probability later when we talk about digital demodulation techniques. Okay, so talking about error probability at this point in detail will not be will not be of much significance unless we know how we are going to demodulate the signal and how we are going to modulate the signal. Therefore, ultimately the final error probability depends on what type of modulating schemes you are going to employ and how you are going to demodulate, what type of demodulator which you are going to use it. Okay, so when we take up a demodulation in detail, we will discuss and come back on the normalized minimum distance. At the moment, just to keep this as a point of information in mind. Okay, ultimately the most important parameter of a signal constellation, which determines its overall performance in Gaussian noise, is this Roman. And mind you, this calculation is completely based on the assumption that the noise is Gaussian. If it is not not Gaussian, then you cannot use this kind of calculations. So this is the most important parameter one has to remember, that is the normalized minimum distance. Okay, so at this point let me stop here, and the next lecture we will continue from here onwards. Thank you very much.